For Chapter 4, the chapter can be divided into primarily two concepts. The first half of the written material is related to how we name compounds, both covalent and ionic, whereas the second half has to do with how we figure out how to do some calculations with those, such as related to molar mass, in terms of how much do these compounds that we have named, what is their mass, so that we can convert between masses and numbers. So let's look at some of these naming rules. So what we're going to start off with is we need to name compounds. So first we have to know, how do we decide what naming rules we're going to use, because we have two primary sets of naming rules with one variation inside those. You have, how do we name ionic compounds versus how do you name covalent? So as a reminder, ionic is going to occur generally between a metal and a non-metal. And this happens because the electronegativity difference is large between these, and they tend to appear on opposite sides of the periodic table, letting you know that their electronegativity difference is large. We divide ionic into two types. We have monovalent. These are also called type 1. These you just name, where you use the first word will be your cation, which you don't do anything special to, and then the second word will be your anion, which you just have to change the letters to IDE if it's a single atom, or if it's a polyatomic ion, you just put the ion there. This has no Roman numerals as part of the name. And we'll look at an example of these in a moment. And then for type 2 are what we call polyvalent. These are going to occur inside our transition metals and p-block metals, not the group 1 and 2 metals. This is because these metals can have more than one oxidation state. They can lose different numbers of electrons, so we have to be told in the name of the compound how many they lost. So with these, in addition to using the cation and anion names, we also have to add a number in Roman numerals that we put in parentheses, and this occurs between the cation and anion, and this tells us what the charge of the cation is, since we already know the charge of the anion. And then we have covalent compounds. We name these using prefixes. So these compounds are going to be the ones where we have a pair of non-metals, and that their electronegativities are very close together, so that they are going to share electrons, rather than in the case of ionic, where one atom is taking electrons from the others. So let's start with our first compound, VCl4. The first thing we need to decide is it ionic or covalent? And in this case, we can determine that this is indeed ionic, and that is because vanadium is listed as a transition metal, while chlorine is a halogen in our nonmetal section. So that means we need to figure out the charge on our vanadium to be able to name the molecule, since vanadium is a transition metal and can have multiple different valencies, so we don't know what its charge is just because it's vanadium. So in this case, what we do is this molecule does not have a charge naturally, so that means the charges of our cations and anions need to add up to 0 so that we get a non-charged molecule. So for here, we'll take our charge on vanadium, and since there's only one, we don't need to multiply it by anything. And to this, we're going to add 4 times the charge we get on the chlorine ion. Remember that since these are ionic, they're actually going to have charges. Chlorine. And this has to equal 0. So we don't know the charge of vanadium. We know the charge of chlorine is equal to -1. That's because it's a halogen, and it needs to gain 1 electron to become a noble gas. So all of our halogens take on -1 charges when they form ionic compounds. So here we have that the charge of V, which I'm just going to write with an X. That way I can represent it as a variable. So X plus 4 times -1 will give us a 0 charge overall. So we have X minus 4 equals 0, and X equals plus 4. This plus 4 means when I write the name vanadium, that after it, I want to write an IV in Roman numerals to represent the number 4, and then we put chloride afterwards. So this is vanadium 4 chloride, and that would be my answer for the first one, because this is a type 2 ionic compound. So let's look at our second compound here, S2O3. So with this, we should be able to denote that sulfur and oxygen are both non-metals. We're going to end up with a covalent compound here, meaning that when we do this, we want to use prefixes in our naming. So this is going to be disulfur trioxide. So this one we didn't have to worry anything about charges or anything because this doesn't form ions, so it's sharing electrons rather than gaining and losing. So we didn't have to go through and try to figure out any charges. So now I'm going to clear this away for more room, and we'll start with NABR next. So, NABR. Again, we have a metal plus nonmetal, meaning this is ionic. But for this one, Na for sodium appears in the first column. That means it's monovalent. So I just need to write the word sodium, and I don't have to do anything with the charges. And then I just write bromide. Remembering that you have to make sure this IDE ending is right because changing those letters will be a different molecule. So it's sodium bromide. Let's go to our fourth one. So again, for our fourth one, we're going to have another type 1 because calcium is in group 2. And we're coupling it with a polyatomic that we know is already in an ionic form. So this is going to start with calcium. And then you have to have memorized your polyatomic ion SO3. So in this case, we're going to have calcium. So we have to remember that it's sulfite. Because if you instead wrote sulfate, that would be CaSO4. So you have to pay attention to these endings, and they're very important when writing our names. So we have one more that's also going to appear similarly here. Ammonium is our NH4 ion, which you have to have memorized. It's the only cation we have to memorize. And since it has exactly a +1 charge with no other options, it's also considered monovalent. So I'm going to write that this is ammonium chloride. And that'll get us our NH4Cl. Now we've got one more type 2 to name here, but this one, because we have zinc, we've got to figure out what the charge would be. So we know that so I'm going to name our charge of our zinc is just going to be written as X. And then sulfur, based on its group, it's a chalcogen. And it's in our group 6A. So it's going to have a -2 charge because it normally has 6 valence electrons. So it needs to gain 2 when it becomes a noble gas-like configuration. So I know that 1, because there's 1 zinc times the charge of zinc, plus we have 1 sulfur times -2 is going to be, we'll put both these in parentheses, that overall, these need to add up to a charge of 0. So we have X -2 equals 0, or X equals +2. This means that we're going to have a charge, it's going to be zinc 2 sulfide. An important, my E fell off the end of this, so DE. There's an important note to make that for my purposes, I'm okay if you name it here, but this may not be the compound you actually find if you were to look up zinc 2 sulfide. What you would actually find is people just called it zinc sulfide. The reason for this is that the zinc ion is only able to take on a +2 charge state. That means it's not actually multivalent. For the purpose of my exam, though, I will accept this answer. But if it was a free response question and you answered zinc sulfide because for some reason you remember it that way, or you know which of your atoms are actually monovalent, even though they're transition metals, I would also give you credit for that. So this is perfectly fine, though, and this is what I would expect you to turn in. I don't expect you to try to memorize which of your transition metals are actually monovalent, but I will make sure to give credit if you give an answer that is technically correct, even though it isn't going through the rules, because you might know one of your exceptions that we had that you could learn. But you don't have to memorize those, so just treat it as zinc 2 sulfide, unless you have some reason to worry about, like you're like, oh wait, no, I know it's actually zinc sulfide. Yes, you're technically correct. This zinc 2 answer is fine, though. So now, what I want to look at is, let's see what happens when we go the other way. So now we have the names, and we're going to have to turn them into compounds. So I'm going to start with lithium fluoride. So what I like to do is check each ion. So lithium is Li, and it's always going to be a +1 because it's in our group 1. And then fluorine's a halogen, and it's always going to be -1. So the lowest common multiple between +1 and -1 is just going to be 1. So this is simply going to be LiF. Because the pluses and minuses are already balanced, exactly 1 electron is going to be taken from the lithium, and each time exactly 1 fluorine will be enough to pick up that 1 electron. So let's look at the second example. So here we have lead 4 sulfide. So we have Pb, and since they write that IV, we know it has to be +4. And then we have S2-. So the lowest common multiple between 4 and 2 would be 4. So the electron exchange we expect between these is that 4 total electrons will be exchanged. To exchange 4 total electrons, you need 1 lead atom, since it's able to give up 4. But the sulfur you're going to need 2 of, since 2 times negative 2 is going to give us our minus 4. So from there, we're going to be PbS2 is going to be our compound here. And that is going to be lead 4 sulfide. So next, let's look at calcium phosphate. Calcium is going to have a +2 charge because it is in our group 2. Whereas phosphate is going to be our polyatomic, and it is PO4 3-. And for this, we now need to look the lowest common multiple between 2 and 3 is going to be 6. That means 6 electrons need to be exchanged. So we have 3 calcium atoms, because 3 + 2 charges will get us to +6. And we will have 2 phosphates, PO4, and we have 2 of them. And that will be our compound here, because this exchanges exactly 6 electrons so that both are able to, the calciums can lose their electrons and the phosphates can take them. Next, we have copper 1 bromide. This will be Cu +1, and then Br is -1. So when we pair those together, we just have to put CuBr. Since the plus and minus are already balanced, we don't have to worry about making any changes. Next, let's look at our calcium sulfate hemihydrate. So we've got calcium 2+, we've got our SO4 2-. So these are already balanced with what we're doing. So we'll be able to, just for that part, write calcium sulfate. But we also have to remember the hemihydrate. So when you see a hydrate, you put a dot here. That means complex 2. Hemi means 1/2. And then the hydrate, we write H2O. So that means our calcium sulfate hemihydrate is going to be CaSO4 dot half of a water. Note that we only did this one prefix-oriented question, but make sure to still learn all your prefixes, as I may give you covalent compounds to switch into names as well, so you should be able to recognize all of them. That includes all the way from mono up to deca. So you had 1 through 10. And then for the hydrates, you also had to learn the hemi, which is a half. So now let's start to combine this where we take the naming stuff, but now let's actually look where we start doing formula masses, so our molar mass type stuff. So I'm going to start with lithium fluoride. So lithium fluoride, we want to know its formula mass. So what we can do is we can take the molar mass of each atom and add them together. So if I look up lithium, lithium has a mass of 6.94 grams per mole. And then fluorine has a molar mass of 19 grams per mole. When we add these together, we're going to get that it has a molar mass of 25.94 grams per mole. So that means for every 1 mole of lithium fluoride, you have 25.94 grams, which you're now going to be able to use as a conversion factor to get between grams and moles, or moles and grams, which we'll be doing quite regularly throughout the rest of the semester. We'll do the same strategy with these next 3 examples. So this is for my lithium fluoride, LiF. So let's look at what it's going to be for my KCl. So here we have potassium, which has a molar mass from our periodic table of 39.10 grams per mole. We can then look up chlorine, which is going to have a molar mass of 35.45 grams per mole. And we add these up, and we're going to get 74.55 grams per mole. So that means for every mole of potassium chloride, you're going to have 74.55 grams of that material. And so the one more like this that just has more atoms. So you have the formula mass of calcium sulfate. That's going to be equal to 40.08 grams per mole, which is the molar mass of calcium. We're going to add to that 1 sulfur, which has a mass of 32.06 grams per mole. And then we're going to add to that, we have 4 oxygens, and each oxygen has a mass of 16.00 grams per mole. Don't forget to do the 4. If you just add 1 oxygen, you'll get the wrong thing, because each of these molecules takes 4 total oxygens to make. And when we do this, we're going to get a molar mass of 136.14 grams per mole. Finally, we have the copper 2 chloride. So you may note here, you'll have to be able to exchange the name into the chemical formula before you can do the formula mass. So here, copper has a Cu, has a 2+ charge, and chlorine has a -1 charge. That means I'm going to need 2 chlorines to make this molecule, since I need to equal this 2+ with a 2-. So this is CuCl2. So the formula mass of CuCl2 is going to be equal to 63.55 grams per mole. Put a line between these. which is going to be the mass of my copper. And we're going to add to that 2 chlorines, which each have a mass of 35.45 grams per mole. Again, make sure you pay attention to the 2. If you named this wrong, you wouldn't be able to get this correctly. Like if you just put CuCl, you wouldn't know to put a 2 there. When we add those together, we should get a molar mass of 134.45 grams per mole. And that's how we're able to calculate formula mass. You're going to do this a number of times throughout the course here. So I want you to make sure you're able to do this pretty well because we're going to keep using it all through Exam 3 and Exam 4. So now let's look at a percent composition question. So here we're asked what percentage by mass of calcium chloride is calcium. So, and note that I might not write this here, although I will sometimes, because I don't want you to miss every single question if you don't know how to name things. But there will be problems where you're expected to just be given the name and know it, but I'll make sure there are also some where you have the thing provided to you in case you miss a naming rule. I don't want you to miss everything for that reason. So, but this is the long-term goal, is if I, as a chemist, I want to be able to say to you what something is without having to write out the letters every time, and you should be able to know that. That's why we're worried about it. So to find our percentage, we need to remember percentages are always parts over wholes. So in this case, the mass of calcium, the molar mass, if I had a mole of it, is going to have a mass of 40.08 grams per mole. So that's my mass of 1 calcium. But then if I were to take the whole molecule and add up the 2 chlorines to it, I would get 110.98 grams per mole. And then I'm going to multiply by 100% since it's a percentage, and that'll change my decimal to a percent. And if I did that, I would get 36.11%. Note that you don't have to worry. I'm not worried about the exact number of sig figs. In this case, since you were given no problem in your answer, I would have given credit for something like 36%, 36.1%, or if you did another decimal, if you had done more with the problem. Note that you can also find the percentage of any of the other atoms. We could also find the percentage of chlorine. So this is of calcium. And if we do this, we should get a number that is very close to 100% with only a small difference in maybe the last digit because of rounding differences. So if we want to do the percentage of chlorine, we would need to know the molar mass of chlorine over the molecule. Now the first thing to take into consideration is the fact there are 2 chlorines in this molecule. That means I wouldn't just have 1 chlorine, which would have a mass of 35.45, but instead 2. So 2 chlorines is going to have a mass of 70.90 grams per mole. And if we divide it by 110.98 grams per mole, if you go through and do the math for that, you'll be able to get your percentage of chlorine, and that'll give you something that is similar to 100% minus this number. So you can do it the setup the same way. That's supposed to be a 9. It doesn't really. I'll rewrite it. So yeah, so we can do the same thing with other atoms as well. Just make sure to pay attention to how much the atom makes up. In our first case, it was just calcium, so that's why we only needed 1, whereas down below, you would need 2 of them. So now we're going to do a problem that's a little bit long in its structure, but is helpful and is very systematic. In my notes, I've gone through an exact way to do this, and I'm going to follow those same steps. So our first step is if you're given percentages to simply turn those into grams, assume you have a 100-gram sample. In this case, though, we gave you numbers, so you don't have to worry about making a conversion. But if you did have percentages, just assume you have 100 grams. So for example, if you had 30% nitrogen, that would be 30 grams of nitrogen. So in this case, we have 49 grams of nitrogen and 140 grams of oxygen. So our problem tells us for step 2, we need to convert this to moles because we want to know an empirical formula. So we want to convert it into the number of atoms that are present in the molecule rather than something about the mass. And mole is the way we get between how much it weighs to what the number of these things are. So we use our molar mass of 14.01 grams per mole of nitrogen for 1 mole of nitrogen. And when you do that, you're going to get 3.50 moles nitrogen. And here we're going to have 16.00 grams oxygen for every 1 mole oxygen. Our grams cancel, and here we're given 8.75 moles oxygen. Notice that I'm writing the atom it is. I'm not just putting 140 grams and 49 grams. This is because you're working with multiple atoms, and I regularly see students not notice which they're doing and reverse them and then getting the incorrect answer. So you need to keep track of what atom or molecule you're working with. This will continue to be a trend throughout the semester as we'll start working with molecules where you're changing from one molecule to another as you're using chemical formulas. So it's a very good habit to get in because you will miss questions if you're not doing that, and that's an unfortunate reason for doing so. So make sure we label things. So this is step 2. Now we know that our ratio is for every 3.5 moles of nitrogen, there are 8.75 moles of oxygen. However, you're not going to see a molecule listed as in 3.508.75. We don't do that. So now we need to get this ratio into a number that is actually an integer that we can use for our molecule. So we're going to divide by the smallest number. And since we're dividing both, or if there's more than two, you're dividing all of them by the same number, you're not changing the ratio. And that's what's important. We need to keep it the same. So I do this division, I'll get 1 nitrogen versus 2.5 oxygens. Notice that we still wouldn't see NO2.5. So we need to get rid of this decimal here. So to do that, I'm going to multiply both by the same number. In this case, since I have a 0.5, I'm going to multiply by 2. And that's going to give me 2 nitrogens, 5 oxygens. So when I do that, I get the empirical formula is into O5. So this is my empirical formula, which answers the top question we had. And that tells me that for every 2 nitrogens, there are 5 oxygens. And we could also name that dinitrogen pentoxide, if you were asked to name it. You could be asked, what is the name of the empirical formula of the compound? So as a follow-up, though, we're now asked to switch from empirical formulas to a molecular formula. So let me erase this part. So now, we're going to take our N2O5, and we're going to see, is this the molecular formula, or do we need to change this? So we need to find the formula mass of this. So this is going to be 2 times 14.01 grams per mole. That's going to be my mass of my nitrogens. Plus 5 times we've got our mass of our oxygens, which are 16.00 grams per mole. And when I add all these together, I'm going to get that the molecule N2O5 would have a mass of 108.02 grams per mole. And you check to see if this number is the same as your molar mass, and it's not in this case. We have 216.04 grams per mole. That means I'm going to need multiple N2O5 units to get to the real molecule. So what we do is we take the molar mass overall of 216.04 grams per mole, and we're going to divide it by our molar mass of 100.02 grams per mole. And when we do that, we should get an integer. In this case, you get a 2. That means that you need twice as many atoms to make your molecular compound. So we multiply both by 2, and we get N4O10 as the actual molecule that we're going to have present. So that is how we get towards a molecular formula from having an empirical formula. Note that you can also do the reverse process. For example, let's say I know that I have S2O4. We can tell me this is the molecular. We can go to the empirical from there. By doing the empirical, we look to see if there are any common factors. In this case, the common factor is 2. If we divide both these by 2, we get that the empirical is going to be SO2. So we're able to do this both ways. We can go empirical to molecular or molecular to empirical. When you're doing empirical to molecular, you'll need some additional numbers, in this case a molar mass, to make that transition. For molecular to empirical, you won't need any additional information. You'll just have to know how many atoms there are, and you can see if there's a common factor. So that concludes what we're going to be working through in this chapter. Make sure to put a lot of emphasis. You want to know how to name these molecules, since it can come up inside other problems. Make sure we can do each type of naming, as in know whether it's ionic or covalent. So you need to know conceptually the idea of metal, non-metal is going to be my ionic compound, whereas 2 non-metals are going to be my covalent compound. And then we have to figure out, depending on the type of compound, what the naming rules are. So for ionic, if it's type 1, meaning it's monovalent, we just have to put the 2 words together with an IDE ending if it's an atom for the anion, and we don't have to change the cation. But if it's a type 2 compound where it's multivalent, then you're going to need to add the prefix as well based on the charge of that. Or in the case of molecular compounds where you have covalent bonds, you'll have to name those using prefixes. So we'll take all that information and then calculate things like molar mass here and be able to find empirical formulas based on the numbers you get from that. And if you can do all those things I just said, that'll finish you up for this chapter and will be a fair amount of the material on the exam coming up in a little bit. So I hope you do well, and hopefully this helps out some. Remember, you can always come and ask me questions if you have them. Feel free to email or to send me a message or to come to my office hours before the exam.